All right, so thanks for the chance to give a talk here as well. So I've given a few talks in this seminar room, but it's a completely new program, a new group, and I haven't been in any of your seminars, so maybe you tell me what you want. So I have about an hour's worth of material here, and what do you normally do?
We typically do 1 hour,
Yeah.
questions included.
Okay.
You know,
So then maybe we need to be a little bit selective. So I'm basically, maybe most of you don't know me, so I am originally a numerical analyst, and I started to get into Bayesian inference by trying to improve the efficiency of numerical methods, in particular Markov chain Monte Carlo importance sampling, variational inference methods, and using the sort of hammers and tools that I'm used to, and one of them is essentially that the fastest or the most scalable methods to solve any numerical problem, in my opinion, are hierarchical approaches, be it fast Fourier transform, multi-grid, etc. So this is, I've worked a lot on multi-level Monte Carlo, and so this is one of the things I wanted to show you, like Bayesian inference, using multi-level Monte Carlo type methods. And the second one is surrogates, and here in particular, low-rank tensor approximation. So neural networks are obviously fairly well known these days. Gaussian processes, I guess, are known in this community, but there is also another set of tools which are low-rank tensor approximations, which can be very efficiently used to do inference. So the starting point for this is to say, I should say, when I mean scalable, I mean applying it to really large-scale problems. So both the parameter dimension can be large, even up to infinite dimensional, and the latent field is something infinite dimensional. The latent field is definitely something infinite dimensional because typically we are talking about some PDE solution or some real process in 3D, 2D, or 1D, but continuous process. And so if you know the process parameters, geometry, everything, input, boundary conditions, then there is a high level of sophistication these days. So I did work on improving those methods, but I find it a little bit boring these days. It's really just tweaking existing algorithms on getting better discretizations and better solvers. And there is software tools to do this. But in parallel, take weather forecasting, which I know is a topic here, and climate forecasting a lot. People now believe that data-driven methods will take over, or some people believe that data-driven methods will take over. This is all about what you do when you want to, when you don't have that much data, when you have lacking data, when you have, if you do subsurface flow, for example, which is this example here, you simply cannot drill the ground everywhere. You'd have a Swiss cheese, and especially if you want to store nuclear waste, you definitely don't want to drill everywhere before. So you want to infer it from uncertain data, and therefore data-driven methods have only got up to a certain amount the possibility to do this. Then the second question, or the second point I wanted to make is that typically we're not interested in the mean of something, and so we want to know maybe what happens as a rare event or something like that. We want to know in the tails what happens. We don't necessarily need the whole PDE solution. We typically want some quantities of interest and want to do statistics on some quantities of interest. But both of those aspects together mean we need to try and combine good methods for assimilating data, for doing inference, with good methods for solving physical problems. And we want the predictions to revert to physics when we don't have data. We don't want some hallucinations or whatever that's called nowadays. So here is just a list of some software that can be used for PDE solving. It's probably not so important here. The important bit is we typically need to tune the parameters. And parameters in the PDE will be usually infinite dimensional. So you talk about the diffusion coefficient in a stationary heat equation, or in the subsurface flow problem, then you need to know that every point in space, which is an infinite dimensional parameter. Geometry also obviously infinite dimensional in general, and typically in order to represent that uncertainty, for example in a Bayesian way, you cannot do it with 5 parameters. You need a large number of parameters, a large number of scales. You need a high dimensional parameterization. So the challenge lies in bringing together the best tools of statisticians with the best tools of PDE numerical analysts, and do that for high dimensional problems where the dependence on the data, most of the quantities of interest that we're interested in, will not be some smooth like the mean or something. You might have a step function if you want to do a rare event calculation. So here is just to set the scene a little bit, what I mean. So I have some data. Data typically will be finite dimensional. You can only measure finitely many things, but it could be very large. You have a model which is describing from input parameters to data, the forward operator, but you're measuring one quantity, and then you want to maybe predict another quantity. So you're measuring, for example, a quantity f of some PDE solution, like this is a tsunami simulation. You might have a buoy here, and you measure the height of a wave at that buoy, but you want to predict what the height of the wave at whatever a town that the tsunami might hit is. So you connect the measured wave height with your model prediction of the wave height, and you, in the simplest case, just simply add additive Gaussian noise, but it could be a more complicated data misfit functional as well. Then you, in the Bayesian setting, put a prior on your parameters, so you don't necessarily mean that the parameter is aleatoric or is random, but you model it as a random distribution, and put into this pi whatever you know. If you don't know anything, then preferably put not too much into there and keep it as agnostic as possible. And then you condition your prior distribution on measured data, on this measured data, and calculate the posterior distribution, which you can use to either do some probabilistic forecasting, as we saw last week, or to calculate some point measure of your posterior, like for example the expected value of some functional of the solution under the posterior. Sorry. And do that, for example, for the mean or the some moment or some other functional of this quantity of interest. So the challenge is we need to do, so this is an integral, if we want to compute this. So the challenge is we need to do high dimensional quadrature integration or approximation if you want to do directly something on this functional, where each of the individual evaluations of Q as a function of theta is a complicated PDE solve that you might need a parallel computer to solve for each sample. So on the quadrature point of view, we have a cursive dimensionality problem because we are talking about tens to hundreds of dimensions, and on top of that we want to do the inverse problem. We want to do the Bayesian setting, so we are actually solving an inverse problem. So we also have problems of stability, or we need to regularize the problem. So the only approach is really, or there's really just two kind of approaches that you can try. You either use a sampling-based method for these high-dimensional problems. You need many solves in order to do, for example, in Monte Carlo, to get any statistical accuracy. Or you try to do a variational optimization-based method in order to get some point estimates, and you can do that via some surrogates, via some neural networks, normalizing flows or transport or whatever, but then you need to worry about how good this approximation is for your true quantity of interest. And then this whole thing, whatever is on here, gets even harder if you want to say something in details. So what's the challenges of doing these conditioned random variables? So if you want to sample from them, it's not straightforward because you don't normally have the normalizing constant. When you want to do expectations, in high dimensions, you have the curse of dimensionality, and even in optimization, it's not always easy to do this under uncertainty. So why is this so? So such conditional random variables, if they're well informed by data, will concentrate. So they will have these sort of long, elongated, sort of banana-like shapes, and you need to sample, optimize, etc. It's difficult for all the tasks up there. You see that typically these problems will have nonlinear interactions. They will not be just simple Gaussians here, these projections. And in particular in these nonlinear settings, then analytically intractable. So let me give you an example that I've worked on, which is radioactive waste disposal. So here we have a nuclear waste disposal site underground, and we want to study what's the probability that but an accidental leak. So these things need to be safe or guaranteed to be safe by the regulator up to 10,000 years. And so you need to actually, you cannot rely on the cask or the concrete around the cask or the chemicals around the concrete around the cask to be holding this for 10,000 years. So you really need to rely on the geology, on the hydrogeology to keep this where it is. You don't want it to be very close to some aquifer where it gets washed into the drink water. And so one of the scenarios they like to simulate in 1,000 years drills down into the repository by accident because they don't remember anymore that it's there, and it goes into the aquifer. And then you want to study how long it would take to reach some safety margin where maybe somebody might get some water out to drink. And so you study this by modeling the permeability, which is the diffusion coefficient in the rock. You model that as a random field. And so this motivating example is trying to show you three things. One, if you want to model the randomness in this field, so this has really been calibrated to some data from a site in New Mexico by Oliver Ernst and others. The first thing is to show you that you cannot get away with 10 parameters. I mean, you can't model this random field by 10 random variables. You really see that the curves with red here are completely off from the truth. So you need to get to hundreds of thousands of dimensions. So you really have a curse of dimensionality. And we've got the prior curves and the posterior curves here. So you really see that you need to condition on data, on measured data of the flow, because otherwise you're off, completely off as well. And then finally, the third point I want to make is that you're not interested what happens here, you're interested what happens here at 10,000 years. So this is log 10. So we want to know what happens in 10,000 years, and so you basically have this this probability needs to be less than 10 to the minus 4 that something leaks. Okay. So simulation is unavoidable because I don't want to wait for 10,000 years, and I need to contend with the fact that these properties are uncertain. So so this is trying to fit it into this general Bayesian framework I said before. Our functional that we get the data from is some functional G curly here of the PDE solution, the PDE that models flow in. So in this particular site in New Mexico, there is essential geology, it's extremely dry, it's in the desert. But there is one layer which is about 100 meters underground. So the repository is about 600 meters underground. There's one layer which is about 100 meters underground, which is the most permeable layer, and it's quite thin. So one of the scenarios they calculate is a 2D flow in this one layer. So you have a 2D diffusion equation with kappa being this uncertain and unknown permeability, which varies. is calibrated. This is an uncalibrated field, but it's calibrated to measured permeability at maybe 60 or 80 points here. And then you also have at these wells pressure measurements. And you want to calibrate it also, condition it also on the pressure measurements. So these would be the Y's here. The pressure measurements would be the Y's. And you can actually use your PDE to predict what the pressure would be at a certain location here. But obviously only with noise, measurement noise, and with an uncertain or unknown permeability kappa. So you put, you discretize this kappa, usually in some sort of Fourier spectral way, like it's called Calhoun and Loew expansion of the random field. And you truncate after d dimensions. And this was this M on the last slide, so a few hundred or 1,000 dimensional parameter space. You put a prior on that, typically a Gaussian random field prior, and then you condition with this additive Gaussian noise model, and you get a likelihood that's of this type. And then you basically want to compute the posterior distribution, which is basically the likelihood weighted with the prior distribution, and then you have a normalizing constant 1 on z here. Now, as I said, you might be interested in, for example, this travel time, which is if something leaks from here, how long does it take to reach the boundary? That would be 1q, and it's clearly a nonlinear dependency on the PD solution. And it's also not the mean of that one you want to know, but the probability that it's below a certain value. So the task, the ultimate numerical task for me as a numerical analyst, is to compute this high-dimensional integral. And typically with a z, with a normalizing constant that you don't know, or that you don't want to compute because that's just as hard as computing the thing itself. Okay. Yeah?
Is it possible that the probability can suddenly change?
Yeah, so you do use geological information. In this particular case, we're only working in one layer, and so it typically is one rock type, and you don't assume it to jump, but you can also model jumps and then have just layered media or something.
It's never like soil, it's always rock. Because soil can suddenly change with.
Yeah. So there is models of that as well, and then the Gaussian assumption might not be so appropriate anymore, but typically the geologists give you a sort of a layered structure, and then you put a Gaussian process on each layer in order to model the whole field. Yeah. So other examples would be locating the source of a tsunami, or an earthquake, doing atmospheric dispersion like the Icelandic volcanic eruption, or we worked with some people from the Turing Institute on additive manufacture and to model the strength of a 3D printed bridge like this one, which is now in Holland. I actually walked over it and I didn't fall down. But there is many examples where these kind of statistical tools are needed for real large-scale physical problems. So the method, and now I need a show of hands. Are you all mainly statisticians here or learners? So this is known, no? Anybody who doesn't know Metropolis Hastings? Okay. So the workhorse is really Metropolis Hastings for doing these large-scale computations, or at least if you want to do it without systematic errors, if you want to do it without surrogates, then if you want to sort of the gold standard, you could say you start with a sample, you form a chain, a Markov chain of states in your probability space. So remember, this would be a few hundred to 1,000 dimensional, and you essentially make proposals according to some proposal distribution, important. So like as an algorithm person like I am, I always look at where is my screw, my knob, and this is basically a knob. So everything else in this algorithm is essentially given. What you tweak is what proposals to choose. How do you pick the next proposal? And you want to do it in such a way that according to this acceptance probability, which guarantees that in the limit, as n goes to infinity, you draw from the stationary distribution, which is pi in this setting of this algorithm. You want this to be fast. So you want it to be fast to converge from, to draw from the right distribution, and you want it to be fairly independent as I go from one state to the next, because the dependence or the correlation between individual states is what determines the efficiency of your statistical estimate, because essentially this integrated autocorrelation time, this number, is essentially, you just have to divide the number of sample size by that, and that gives you how much you lose in efficiency over having samples directly from the distribution, IID samples. So you reject when the thing is very unlikely. So you've got the likelihood, or especially if you make the Q, which is one thing that I would straight away say, I'm not going to talk about that, but you want to make this prior reversible rather than symmetric. So if you made it symmetric, then this term here would fall out. But if you make it prior reversible, then essentially you have likelihood of x divided by likelihood of theta n standing here. And so essentially I can really talk about the more likely one. If it's not very likely, it will get rejected, most likely get rejected. And you sort of pick states that are more likely, essentially, under this prior reversible proposal. The other second thing, but again, as everybody knows here, is in comparison to rejection sampling, you don't throw away everything that you reject. You actually use it to weight the states that you come from, and in some sense, if you can't move away from a place, then you're probably at a very likely place. Okay, so what are the good things? It's very simple. I've literally written the algorithm down, and it's extremely easy to compute. The hard bit here from a numerical point of view is that this involves my PDE solve. So I don't want to do that too often, and I certainly don't want to do it too often when I afterwards reject the thing, because that thing is really not used. The rejected samples in this algorithm, in this basic Metropolis Hastings, are not used. So you create a Markov chain, which means, as I already hinted at, that this thing actually can be used for inference, and it does converge asymptotically to the correct average. If I use samples from this Markov chain, you need to make sure that the kernel that it describes, or the kernel that it describes, sorry, is in detailed balance, and under mild conditions, as I said, it converges. The big challenge is that if pi is computational challenging and you reject it, then that's very costly, and in fact it might make it completely unusable. And the states, if I can only make very small. So there is one tweaking parameter, which I didn't talk about, which is sort of hidden in here, is if I make extremely small steps, then of course the chance that I accept is high, but then I will not explore the probability space very fast. It's not mixing very well. If I make very big steps, there's a good chance that I get rejected. So you want to kind of get the best of both worlds, make big steps and not get rejected. And the second thing is difficult to parallelize because, as I showed you, it's a chain. So essentially every state depends on the previous state. So we've worked a bit on that, but I'm not going to talk about that today. So I want to use hierarchies. If I want to use hierarchies, I essentially, there is a very simple lemma you can very easily see, is that, so the original algorithm, I think, was never in a paper, or I couldn't find a paper. It's in a book by Liu in 2001, I believe. Is a book where he called it the surrogate transition method. And if you have a surrogate, pi c, so you've got a distribution pi c, which you can really think of as what you probably are familiar with, a surrogate. Something that's almost like my pi, that I've created somehow. Then actually you can use it sort of as an independence proposal from this pi c within Metropolis Hastings. Then the acceptance probability 1 here becomes, in that case, nothing else than this acceptance probability. And you can show that this is in detailed balance with the fine with the real pi that you're interested in. So if I could get samples from this pi c, then in a sort of second step, and this is what this algorithm I'm going to show you now, which is called delayed acceptance, does, is it has like two stages of acceptance. It has the first acceptance step, or the first algorithm that produces the pi c, and then it does a second stage acceptance step where it just looks at this. And the idea of how to do this in the multi-level delayed acceptance is to simply use a hierarchy of models. So I told you that in my case, the models are themselves infinite dimensional. We cannot work with infinite dimensional models on a computer. We need to discretize them. So every PDE solve that I so far have only abstractly called a PDE solve is solved on a grid. It's solved on in some software on a grid. And this is one thing that I find very important to always highlight, especially when talking to statisticians, is typically when statisticians interact with applied scientists, they get given a code, and then they get told, with this mesh size, you get roughly the right accuracy, and go away with that. So I'm saying, if you actually allow yourself to be a bit more intrusive and say, I'm aware that I have a whole hierarchy of meshes that I could run my simulator with, then I can use that. So rather than only using the mesh size that the application scientist gave me as the one he wants, I can also use coarser ones. You could also use finer ones, and you could refine your calculation. But let's say this is the one you're interested in. You allow yourself to have coarser ones, and these coarser ones I'm going to use to produce my pi c, my coarse one. So for today, let's just talk about two levels. So we've got a fine grid and a coarse grid. And we could also have fewer parameters, like we could reduce the D or the M I had before. Instead of having a 100-dimensional problem on the coarser level, I only take a 20-dimensional one, for example. Or I could only take a subset of the data, which does some sort of tempering, which is also very useful. So all of those I could do to describe my coarser model. So now I have the fine and the coarse, and I've got this lemma up there. So I'll do a little sidestep to where we came from. So at the beginning of the millennium, we had sort of this multi-level Monte Carlo came about, and I did some work with Mike Charles where we used it for this exact PDE application I presented before in the forward setting, in the IID setting. And there you can basically see that if you treat the coarser models as control variables of the finer models, and you write your expectation, even if it's a nonlinear function of the parameters, if the expectation is a linear operation, so I can write it in this way, and I can just simulate each of these expectations separately with my favorite estimator. For example, if I use Monte Carlo, then essentially I get the following phenomenon. On the finer level, if it's two levels, on the fine level, I have the variance of the quantity of the difference going to 0, and so the number of samples I need is small because it's controlled by it's guided by the variance. On the coarsest level, I don't have to, even for more accuracy, I will never have to change my model. My model will be fixed size, will be order 1 size. It will be a coarse model, let's say a 9 by 9 grid, and each sample costs me a fixed amount of cost, but I need to use as many samples as I would use with a normal Monte Carlo.
So when you go from coarse to fine, does the coarse mesh have to be a subset of the fine?
No, no. I mean, for some theoretical results it might be useful, but it's absolutely not necessary. No. And in fact, this is what I meant by this is nonlinear. So you really simulate here on the fine and you simulate here on the coarse, and then you evaluate the quantity of interest. So really you have to think of this as being after you've done all the calculation and evaluated your quantity of interest.
But you have to subtract the same parts. There will be some interpolation of some sort, right?
There is an interpolation in the sense that the sample you calculate here and here needs to be computed with the same parameter. So the parameter needs to be able to interpolate between the two because you want to do a strong coupling between the two. So the crucial thing now is while Monte Carlo for this problem would be essentially the cost of number of samples times number of grid points, so n times m, this algorithm is the maximum of n and m. So it's basically, if I've got to do 1,000,000 samples of 1,000,000 grid cells, now I have to do some constant times 1,000,000 plus some constant times 1,000,000 work, which is a lot less. Yeah.
So even for the same parameters, you want to do more core simulations and fewer fine.
That's right. Exactly. So the crucial thing here, which I'm doing this way too fast for people who have never seen this, the crucial thing is here that by splitting it in this way, you can choose the number of samples differently. That's exactly the right. Sorry, I was way too fast. So the whole point is that exactly you do very few samples on the fine levels and and a lot of samples on the coarse. But this argument here was supposed to say the number of samples on the fine doesn't have to grow because we let the variance go to 0, while the number of samples does have to grow on the coarse, but there the cost per sample is fixed.
How do you subtract? Because I imagine you subtract for the exact same parameters.
But it's just the quantity. So you compute, for example, this travel time on a fine grid, and you compute this travel time on the coarse grid, and it's just two numbers.
Different parameter values.
No, for the same parameter value. So I parameterize my coefficient, and then I solve on a course, and I calculate what for that particular row of the random field, the travel time, the time it takes to go through, and I do the same on the fine grid. And I just get two numbers.
But it's with respect to one set of like the PD or coefficients, parameter and the model parameters. So
I don't need to subtract the model parameters. I just need to. Yeah. But the output is not the parameters. Okay, the parameters could be an output, which is very often in statistics. You want to do statistics on the parameters, but I'm thinking of some derived quantity. But it could be also the parameter.
Corresponding to that parameter.
Yeah. I think she asked before about the nested.
Yeah.
And I think where we are now is that it's nested. If you take two successive levels, there is a nest, but not between the different increments. Right. So you do the same simulations for QL and QL minus 1, but not for QL and QL minus 2. But when you look at two successive QLs, then you have to compare.
Yeah.
Yeah. Maybe I explain it to you afterwards. I think it's just because I'm probably haven't put the detail here that it's. I think it's pretty straightforward. I can explain it very easily after. The crucial thing is that if you're going now into an MCMC, a metropolis setting, then we're here, and this might go in the direction what you're asking. So in an IID setting, I just can draw a sample, and I pick the sample, the parameter, and I pick it for this calculation and this calculation. Yeah, and this is the same parameter, and I compute two numbers, and I do that, whatever, 1,000 times, and I average. Here now we have the problem if we want to do this with respect to the posterior distribution, then we have no access to directly simulate from the sample from the posterior distribution. We can only do it via a metropolis algorithm, and so we get a chain of samples, and the coarse chain is conditioned on the likelihood of the coarse. So it's not conditioned on the same likelihood than the fine. So I cannot just stick these two under the same expected value and subtract. Yeah. Okay. And so in the metropolis setting, you really need to compute two expected values separately, but you want to do this by correlating the chains, because otherwise you don't get any strong convergence. And so there is a specific way how you can correlate the chains. And in the first paper we wrote, we did this simply algorithmically in such a way you run a chain on the course, and this is your chain that just runs. And occasionally you take one sample to propose to the fine. And then you accept, reject on the fine, and you let the chain on the bottom continue running. Again, you accept, reject, and because you don't need as many samples on this, Then for the course, this is enough samples to compute. It's cheaper because only every 10th sample gets computed on the fine, and that's fine. The problem is, if you do that, because this state does not go back, or when this state goes back to this state does not go back to that state, this algorithm actually is not Markovian. And so it actually is very hard to prove that it's theoretically correct. It's only theoretically correct in the limit as the subsampling size gets to infinity. In practice, though, it's this biasing error that you get from this not Markovianity is minuscule. So in practice, this algorithm is still my favorite algorithm because it's a lot more parallel than the other one I'm going to propose to you in a minute. So the second problem is if the likelihood on the course is actually too far away. If you've got too crude a model, then you might not even overlap anymore very well. And you might have a problem that any proposal you come from here, which is a perfectly fine proposal here, is extremely low likelihood on the other one, and you reject. So you have to reject a lot of times because your models are just too far from each other. So in our PDE examples, as long as you take the mesh size fine enough, you will not be in such an extreme situation, but it's still something you have to worry about. So this is now this adaptive multi-level delayed acceptance that we did subsequently. And this now is a proper Markovian algorithm. And the only difference is, while here you have to sort of think of a bottom-up approach from the coarse to the fine, here we think of a top-down. So you really are producing an algorithm for your fine Markov chain. But in order to get the next proposal for your fine Markov chain, you actually dip down. And you make a subchain on the next lower level. And you have your kernel of this Metropolis Hastings algorithm on the course. And you let that run for a while, a subchain. And after j steps of that subchain, you take either the last proposal, the last state is a proposal, or you randomize. Both are possible and have the advantages. And then you make this a proposal for this algorithm, for the final level. The difference now is, if this gets rejected, then actually I go back to this state and I make a new subchain at the bottom. So I really reset my whole algorithm. So it's Markovian, and it samples correctly from the bottom one samples, the top one samples correctly from pi f, but the bottom one, because it gets always conditioned on a state from the fine chain, is not really from pi c. So here you have the problem that the coarse one is not sampling from pi c. It samples from, as Colin Fox always calls it, the bastard distribution, some sort of bastard child of the two, which is somewhere in between. But you can prove that still it's fine, it's a good distribution. It's just some empirical distribution coming from the states of this j times applying the kernel to a fine state. In the limit, this converges, so this converges to a valid distribution. And the cost saving is still, as in the multi-level highlighted at the beginning, that the difference between the cost of sampling on the coarse, on the fine over the coarse is essentially what you save in terms of cost. Okay, and if you can prove that this acceptance rate, if the two models are close, then you can prove that the acceptance rate, so for this algorithm we actually proved rigorously that the acceptance rate goes to 1 as the mesh size goes to 0, and you can prove a similar result here as well. And so the acceptance rate of the second proposal, it's very, very rare that you will reject. Basically you have integrated autocorrelation time being close to 1. And it generates a Markov chain because it's Markovian and in detail balanced with pi f from the lemma I showed you before. And if you randomize the one you pick from here, you can actually do the multi-level variance reduction as well. Okay, so this would be the algorithm. You have this coarse density, you've got the fine density, you have a proposal for the coarse. This is just your proposal for the course now, because on the course level, you run your favorite Metropolis Hastings. I don't tinker with the course. And then once I have run the subchain for j steps, I propose it as a proposal for the fine, and then I use this acceptance probability that I had in my lemma 1. So the two, if I've got two commuting kernels, there is just a lemma, then the composition, and each is in detailed balance with pi, and the composition is in detailed balance with pi. Therefore, our algorithm actually simulates or is in detailed balance with pi f. So here's a quick proof, which I'm going to skip for the sake of time. So as I said, if you randomize which of these samples in the subchain you choose as your proposal, then you can actually do the variance reduction again. So instead of having expected value of pi c plus expected value of pi f minus expected value of pi c, I now have to do expected value with respect to this tilde distribution, which is essentially the application of j times the kernel of the course onto the fine in the limit asymptotically. And it's irrelevant that that's not pi c, and you can use it for variance reduction as in the multi-level Monte Carlo algorithm. Yeah, this is what I meant. So instead of having pi c here, I have my pi c tilde here. Here also my pi c tilde. I do all the samples, so this would be n times j max samples, which I do on the course. So this is as many times as I go to the subchain, plus the length of the subchain. And I average that. That's my course estimator. It's an estimator with respect to pi c tilde, with the empirical distribution given by those members of that chain. And here I'm essentially taking only n samples, calculated on the fine, where I subtract the randomly picked one from the course. And so this is j max times fewer samples. And this is because I've randomized how I pick these. This in the limit as little n goes to capital N goes to infinity. This is the same average as this. So these two averages cancel out again. So we're trying to do. Oh, this is a too long ongoing. I should take this off this slide because we simply don't get around to it. We wanted to do some proper formal proof of this. That this converges rigorously with respect to the mesh size. Maybe I need to get a new student to do that. The second point I told you was that what happens if this course distribution is actually too far away from the fine. And here you can essentially think of calculating, because you get samples from both, you can use these samples in order to do a correction. And you could do many things. You could train a Gaussian processor on the correction. You could do a neural network. But actually, it turns out that a simple Gaussian correction, so simply calculating essentially a shift for the mean and sort of a rotation for the variance, and maybe even slightly overinflating that, is perfectly fine. Gives you very good corrector, and you get that very cheaply from the samples you have anyway. And so we do that, and you can then figure out what the corrected course distribution would be, and it's just the original course likelihood plus this Gaussian correction. And because we have the Gaussian likelihood model anyway, this just gets very simple also algorithmically. And you can do that for multiple levels. I've only talked about 2 levels, but you can pass on these correctors all the way up from the bottom. So here's an example for some gravitational calculations. So you've got integral equation. You want you measure the gravitation on the ground, and you want to know on the ground what's there, what type of rock or what type of density. And you've got the signal here. This is the noisy one that we get given. We take a fine model which resolves quite well, and a coarse model where you can see the pixels here, 100 by 100 or 20 by 20, and we say one is the fine, one is the coarse. We model the we use a Gaussian random field prior, and we use the first 32 KL modes, so the first 32 Fourier modes, and then we use basically these two models in order to do our multi-level delayed acceptance. So we compare this here against classical random walk on the left, and you can see that for the 0th parameter, so the first parameter, and the 8th parameter, or then it says 7 here, maybe I got it wrong. So anyway, you see that this is certainly here it's very sticky still. It's not mixing as well as you would, while for the multi-level delayed acceptance you get much better fuzzy caterpillars, and you see it also on the effective sample sizes here. So much higher effective sample sizes, especially for the larger parameters. Just to show you that the error correction is necessary or works. So this is not something I would normally use. So this is a very, very coarse 5x5 mesh. When here I have 25 Fourier modes for my diffusion coefficient, then a 5x5 grid just doesn't really resolve the field. But you can still use it as a coarse model if you use this Gaussian error correction. So here the diffusion coefficient is modeled by Gaussian random field, the first 25 Fourier modes. Oh, sorry, M is a different M here. Pressure divided M, this is a different M. Here, 64 KL modes. We measure the pressure at 25 points here, and we want to do the Bayesian inference on those 25 pressure measurements with the noise, measurement noise 10 to the minus 4. And you see if you use no adaptive error control, you get an integrated autocorrelation time of 122. So you only get about 300 samples for any 40,000 samples independent, while with the error correction you can gain almost a factor 3 just with this error correction. There's a code if anybody wants to try this, tinyDA. Okay. Any questions on this? Yep.
So is this all in the multi-level setting rather than multi-fidelity kind of?
So like I said, at one point, it probably went under. The multi-level is for me multi-fidelity. So you can just choose what you want on the coarser level. It can be fidelities if you want. You can, in fact, what we do these days a lot for example, astrophysics, is we use a Gaussian process on the coarsest level. Okay. Because the coarsest level becomes when you've got very few levels, it's actually the coarsest level which becomes your limiting factor. Mm-hmm. And so we use a bunch of samples on the coarsest level to train a Gaussian process on the coarsest level, which we can then use like tons and tons of samples of. And then we correct the Gaussian process with the coarse model, that's our first level. And then you can add finer element models on top. Yeah. Yep.
So when you mentioned the Carnot of expansion, is that similar to stochastic finite element? Or is it?
Yeah. So I mean, we don't use it. So stochastic finite elements would be that you then actually use finite elements to solve it. Yeah. I'm just using it to parameterize it. And then I draw samples from my Monte Carlo. Yeah. But it's the same.
It's not a question, but I was thinking, when we do MCMC, we reject the burn-in period anyway.
Yeah.
So instead of doing course find right from the start, is it possible to start from the course?
Yeah. That's exactly what we do. That's another point, a very important point, that of course the whole burn-in is done on the course. Yeah. So I don't go up until I'm already burnt in on the course, but typically we actually do reduce the dimension when we go from coarse to fine. And so you need to burn in the fine modes. So if I take, for example, my first 50 modes on the course, and then I take 200, then those 150 that I've added, I need to burn in. But it's a lot faster to burn that in.
But you cannot go on the L, you cannot fit your Gaussian.
No.
You fit it
later. So I realized that I've already used 45 minutes. So here is just one more slide, which is not MLDA, this is the old MLMCMC, just to show you for a real, much more challenging diffusion problem, this is what the famous precondition Crank-Nicholson that people use for theoretical results a lot gets. So for this problem, you get an integrated autocorrelation of 4,100, which is humongous. I mean, it's like, so Colin Fox always says it's like, it's as if you would tell a PDE person to solve a finite element matrix with Jacobi method. It is the Jacobi method. So PCN is the Jacobi method, and you would never solve a finite element system with Jacobi method. If you use this likelihood-informed subspaces of Tiangong Sui, which basically calculates in some directions that are informed by the data, sort of an appropriate approximation of the covariance, you essentially can reduce this already by a huge amount. And in this paper that I did with TC, we combined this with the multi-level. And you see that then you use this as your coarsest level, and then you, on the finest level, you'd have an integrated autocorrelation of almost 1 or 1.8. So the green one here is the Dili algorithm, and this would be multi-level Dili. Yeah. So this is just to show you, because people were criticizing our method that we start already with a crappy method, then you compare yourself against the crappy method. So this would be the crappy method, PCN. This would be multi-level, what I described before, with PCN on the coarsest level. And the single level Dili is actually better. So you really want to combine a good coarse sampler with your multi-level. Okay, so I will basically just flash this up now and then not take more time from you, just so that people who are interested can come and speak to me afterwards. So basically, the second approach I was going to describe, or was thinking about describing, is measure transport. So people are familiar with normalizing flows. If I want to sample from a complicated distribution, I can sample from a simple distribution and learn, for example, by minimizing KL divergence, now the other KL, Kuhlberg-Leibler. By minimizing KL divergence, you can minimize, or you can compute an approximate map T that approximates this mapping from this density to this diffeomorphism. But we know how difficult it can be to train neural networks. We know how fallible it can be, and there is also other problems with that. So there is kernel-based methods like the Stein variational methods, there's polynomial type methods, etc., etc. But there's also a thing called low-rank tensors. And they can also break the curse of dimensionality. So we've worked a lot on that, and I'm happy to tell people. It's something that is well tested. It comes from the quantum physics community, and it's used there for high-dimensional quantum entanglement, or disentanglement, rather. And this has been formalized by Ozeledets and Tetishnikov as a general approximation tool. And then there's also work by Hackbush, where they've developed a whole family of such methods. But the most simple tensor chains can be used when you want to sample from a high-dimensional distribution, which could be a posterior distribution. You can basically think of doing a conditional distribution method, so writing it as a marginal and then conditionals, so triangular transport. So this is literally marginal of x1, then x2 given x1, etc., etc. And if you have this, if I had these d functions here, these d densities, then I can basically have a very simple algorithm to draw samples from this multidimensional one. It's just unraveling this triangular transport. You sample from the first distribution here, for example, here from a uniform to this distribution, it gives you 3 points. Then conditioned on that 3 points, that's these 3 lines here, you then draw the second dimension again uniformly, and it draws uniformly along that line, but conditioned on this distribution along that line. And you can do that up to d dimensions, no problem. And the problem is how to get these guys. And this is where tensor chains come in, which I absolutely have no time to describe, but it's basically it's a separation of variables on steroids. So it's basically what you've learned in school or in first year maths or second year, if you want to solve a PDE or something, you could do separation of variables. And so here again, you can do separation of variables. You can think of, so the simplest way of computing this is with an SVD, with a singular value decomposition. And you can really think of taking the first dimension against all other dimensions. So you just make out of the tens a very, very long matrix, and you use SVD on that. That has separated your first dimension from the rest. And then you can recursively apply that algorithm for the second to the dth variable and do the same thing again. And that's what this is supposed to say. So you split off one variable, you split off the next variable, you split off the next variable, and each of these splits you can think of as SVD. It's a hierarchical SVD. But if you've got n to the d entries in such a tensor, then think of just some small numbers, and you will already notice that n to the d is unhandled. You can't handle. So you can't do SVD on this. But you can do what's called cross approximation. So this is the SVD root, which in 2D works perfectly fine, and that's what everybody uses for doing low rank approximations in 2D. But in higher dimensions you cannot, but you can use this cross algorithm, which in pictures looks like this. You randomly pick three. I want to do a rank 3 approximation. So I pick 3 columns at random. I only evaluate those 3 columns. So that's 3 times n evaluations. And then I calculate the maximum determinant of any 3 by 3 matrix in this 3 by n matrix. So you calculate the determinant, the 3 by 3 determinant. And the one that maximizes that, which can be done linearly in D and in N, you then pick those 3 indices as your row indices. And then you forget your column indices, which were randomly chosen anyway, and you evaluate along the rows, all of them, again, n times 3. And now you do the same algorithm again and again and again and again, and it can be shown that that converges, and it converges to a quasi-optimal rank 3 approximation of your matrix. And this whole thing can be done for tensors by rolling out your matrix into long thin and doing it hierarchically. And it's linear in D, it's linear in N, it's polynomial in R, in the ranks. So obviously you need to control the ranks. And that's where the theory comes in and the work comes in. But in practice, I can now use it for my conditional distribution method. Because, so normally you'd need to marginalize, which is again a d minus 1 dimensional integral. So you haven't won. Here you've got d minus k dimensional integrals. I haven't won anything. But with this tensor train approximation, actually you can figure out that all the ones that I'm conditioning on, they're just evaluations of univariate functions. All the ones that I'm marginalizing over are just one-dimensional integrals. And there's only one, maybe the kth one, that is sort of really random still. And so in order to sample from that, you just need to do a 1D CDF inversion. And all that can be done linear in D. So you can use that then for variational inference directly, because any integrals you want to do over any functionals would be just a sequence of 1D integrals. You can do conditional sampling. That was the what we discussed about for neural networks. You can do that with these guys as well. Then you can use it as a surrogate for the multi-level delayed acceptance I just described, or you can use it in importance sampling for ray events, which is the example I had prepared. And there you basically then simply estimate the numerator and the denominator. You calculate biasing densities for the numerator and the denominator. So the optimal ones. This would be the optimal for the numerator, and pi would be the optimal for the denominator. You just calculate 2 of such approximations, and then you can do, for example, this travel time calculation I had. If anybody is interested, I can give this a slower version of this. The last thing maybe to highlight is that, of course, all these densities in the posterior in the inference setting are concentrating. I've said that at the beginning. And so, as you can imagine, if I want to simulate a not grid-aligned, very peaky function with a low-rank approximation, it's not going to work very well. And so the ranks shoot up. So what we do for doing peaky distributions like these ones is we basically do a deep version. I don't like the term, but that's what my course has coined. So you essentially don't push it directly from the reference, this is the reference, to target. You push it first to a tempered version, which looks like this. And then you push it from that tempered version to that tempered version and so on. So you nest several of those. And that is all algebraically very straightforward to do. It doesn't cost you much more than a one-layer version. And that can be used then, for example, to do posterior rare event calculations. So really, calculations of 10 to the minus 4 accuracy in these subsurface flow problems. Okay, so I'm a big fan of using hierarchies for any numerical calculations, in particular for inference. And so we're doing some more work on this MLDA. There's also a multi-grid Monte Carlo that we're working on. I wanted to show you this quite efficient, from quantum physics inspired way of doing surrogates also for measure transport. And this can also be used for operator learning. And if you're interested, I think these slides become available anyway. There is codes, GitHub repositories were given for all of the things. And then we have this easy integration of all codes that I've said in this Umbridge uncertainty model bridge code by Linus Selinger, which we published in this paper recently. That's it. There's some references.
So I'm going to describe a problem which is similar but not the same. So I'm interested in doing an inverse problem where I know that there's an anomaly in the pattern. Mostly homogeneous, but somewhere there is a problem.
In the anomaly in the what? In the
parameter field.
Okay.
So, but I don't know where that is.
Okay.
And it's also small, so it will only show up in the fine resolution.
Okay. Yeah.
So
I think unless you already have the distribution for the one without the anomaly, then this is probably quite suitable because you can already do all the hard work without the anomaly, get a good posterior without the anomaly, and then add the correction with the anomaly.
But the correction where you add would, because I don't know where that is. So I know it's small, but I don't know where that is. So, and it does affect the entire solution. So this was a static.
Yeah.
Yeah, we have electrical wave propagation, for example.
Oh, okay. Hyperbolic problems are always harder. Yeah, sorry. I agree completely. But I think it'd be very interesting to see. So
I worked on tsunamis also. So, I actually did a problem where there was an earthquake caused under the seabed, very close to the shore. In that case, the waves are very high and it's very quick. So this can be similar. And the inverse problem was to detect the source of that.
Yeah. So I'd be interested to talk to you because in my second line of research, I do multi-scale discretization methods, which are particularly geared towards that sort of stuff. Because so we did specifically in carbon fiber composites for aircraft, you have wrinkling defects, which you don't know where they could. Yeah, they could happen anywhere. And so what you do is you first do a localized model order reduction where you get good basis functions of the pristine material, and then you only need to locally do something to calculate new basis functions, and the calculation of the global solution is then fairly straightforward.
Is it called the delamination problem? Similar?
Yeah, that's the application, but the method is, I can tell you about that method. I mean, we want to use it for Helmholtz, we want to try it already. Well, Maxwell obviously would be the next step. So for Helmholtz, when you have seismic and you have multiple noise sources, I mean, when you do the inference, you can, with this method I just described, I can solve all of them in one go. So I once set up my method, and then for each of the sources, I just need to solve very close, small local problems, and I get the global solution. So that might be useful for that.
The linear shallow water, you can just superimpose, right? So
yeah,
yeah, but
I'm interested.
yeah.
Very interested, yeah.
tensor train description, you said that you flatten a tensor and then you essentially do SVD
Yeah.
across.
Or something else.
Isn't flattening a computationally very expensive operation?
No, you just conceptually flatten it.
I see, conceptually.
Yeah, that's exactly what I meant. If you were to do it with SVD, that would be super expensive. But from this argument I described, remember when I just two random columns, you just literally pick. So if I've got a three-dimensional tensor, I pick a j and the k value, and then I just evaluate all I values for that j and k. So that's why I don't even need to change the storage of my thing. I'm just evaluating at particular places. Yeah. But it's a good question.
That's right. The references you put on the last part 2 of the talk, which is a good starting point.
Yeah, this is one thing I wanted to actually say. Karina is already invited by David, and she will talk about that probably, or at least you can ask her to, which is exactly using and giving you more detail on this tensor train approximation in a very important application, I mean optimal experimental design. Because we basically, with this approach, we can essentially build a surrogate of the information gain, and then you can just minimize, as if you had a Gaussian where you have a closed form, you have a tensor train closed form of the surrogate information gain, and then you minimize that, and you, in particular in a sequential design setting, it works extremely well, because we basically, in a follow-up paper to this, we did several thousand dimensional problems where essentially you first do a model order reduction, you decide which directions are the most informed or are the ones that you care most about. In those directions you use the tensor train. You then do the minimization of the information gain. You find the first sample, you sensor, you draw, and then in the next thing, the whole subspace might rotate into a completely different direction because you now have been informed in a certain direction, and that works extremely well. So we can do quite high dimensional, non-Gaussian Bayesian experimental design.
All right. Thank you again.